And good morning, everybody, or afternoon, or evening, or middle of the night, or whatever it happens to be. Thanks, Andreas. So, I had a bit of computer drama this morning, and I didn't think that the stream was going to work, but I got it working just in time. I was just frantically dragging things around and getting it all set up right before I hit stream. So, hopefully there's not too much chaos and things work. Just before I get into the projects again, I just want to do a quick update on some things that might be of interest to my Patreon supporters. Now, what you might have noticed is a few videos ago, like in terms of main episodes, not live streams and impromptu things, was that I began giving away projects at the end of episodes. So there were a couple of videos where I built something and then I picked someone randomly from my Patreon supporters and sent it to them. So, if you're a Patreon supporter, it meant that you could randomly receive the actual project that I showed on the video. I did that for a few videos, and then I found out that that is actually in breach of Patreon's rules, because doing that is considered to be like a raffle or something. It's saying someone is paying for the potential to win something, and therefore it's technically it's illegal. So I thought there wouldn't be a problem with that, but oh well, I couldn't continue doing that. And I've heard of other people being kicked off Patreon for doing it, so I thought I shouldn't. So what I've been doing is trying to figure out other things that I can do for Patreon supporters. I've already got discount codes that go up there, and right after this stream I'm going to do a post to, like a private post to Patreon with the latest discount code, which I've already set up. It's ready to go, you just don't know what it is yet. And I will probably end up doing things like live streams for Patreon supporters only, and then later they can go live publicly and everybody can see them. But I don't know, I'm just trying to figure out ways to say thank you to Patreon supporters, because I really appreciate the fact that people do support the effort that I put into doing this. It might only be $1 or a couple of dollars a month, but that all adds up, and that really helps. So let me see. So we got someone from Denmark, someone from Holland. I know I've got people from Australia because I saw Unexpected Maker right at the top. Hey. And people from all over the world. Before I get into the projects, let's see. Duncan asks, would LoRa be a practical proposition for CubeSat telemetry? That's a really interesting question. I've never thought about that. Whether it is possible would take a bit of investigation. Whether, in terms of whether it's technically possible, whether it is allowed is another thing entirely. The transmissions that you can make from satellites are very highly regulated. You can't just put a transmitter or a transceiver in a satellite and send it into orbit. Everything has to go through approval, and that is to prevent any problems with systems causing interference to each other. It's an environment that costs a lot of money to get things up there, and there's a lot of critical stuff in orbit, so you don't want someone sending up a rogue transmitter that then causes interference on other devices that are up there. So you need to get approval for specific frequencies and power outputs and all of that sort of thing before it can go into a satellite. So it might work. I don't know. What's the range? Well, you'd need to get a range of probably 300 to 400 kilometers. Now, one of the other things about... I'm going to get to ArduSat and LibreSat, etc. later on, so maybe I should answer these questions later, but communications with satellites is a really big and surprisingly interesting topic, and I think I'll get into that later. To do it right, it ends up almost being like a cell phone system where you have cell towers located across an area, and you have a phone moving through it, and it's being handed off from one tower to another. That's essentially what happens with satellites, because in low Earth orbit, circumnavigate the entire globe about every 90 or 92 minutes. So, okay, I'll move on from there. Someone says, I want to make a CNC router, but I don't know what motor stepper I use, NEMA 23 or NEMA 34. That is totally up to what you're going to be cutting. If you're going to be cutting hard material, by hard I mean aluminium and things, not necessarily even steel, then it needs to be extremely rigid. You need lots of torque. If you're just doing things like PCB milling, then tiny little steppers will do the job just fine. But that's getting off the topic. So, although there are some CNC controller projects coming up, in fact there is a project in C in my list of projects called CNC Plotter, so maybe I'll talk about it then. So, looking at my list of projects in Eagle, and we'll flip back to the desktop. So, last time I started up here and I got down as far as here, and then AVR 28 ZIF. Now there's another one in there which is a new project that has appeared since last week, but it's a proprietary job for a consulting customer, so I'm not going to talk about that. Now, I probably should have shoved it off into a subdirectory to keep it hidden. Accel Wi-Fi. Now, this one relates directly to a Superhouse video, and let's have a look at it. Now, one of the videos that I did quite some time ago was about electric window motors. So I've got in our house we have a conservatory which is, how many segments? I can't remember. 12 segments? Yeah, 12 segments, or 12 windows that go around it. So the end of the room is curved, and 4 of the windows open, and I've got little motors attached to them so that the windows can be opened and closed. Now those window motors come from a company called AXA, and they have built-in support for LIN bus. LIN is a simplified variation of the CAN bus that is used in cars. LIN is typically used in cars for simple serial communications between devices. And in fact, the classic use for it is for the vehicle management system to control the electric windows in the car. The motors themselves have a LIN interface on them, and then the vehicle management system, when you press the button on your door to open and close the window, what's actually happening is that button is being detected by the vehicle management system, which is then using LIN to send a serial command to the motor which is mounted inside the window, and that's what makes the window go up and down. So if you've got a reasonably modern car, like by modern I mean anything in the last 10 years or so, it's probably got LIN bus in it. And the domestic window motors that I use have LIN support. So in one of my Superhouse videos, I showed how to make a LIN interface module that allows you to send commands to the window motors and then open and close them. Now that is kind of okay, and I've been using it ever since. It still works. I've got the controller mounted up next to my switchboard, and from my phone or from buttons on the wall I can open and close the windows, and they can be controlled based on rules like related to building temperature or whatever. Weather conditions, wind speed, if it gets windy, have the windows close automatically. But I wanted to do something that would take much more direct control over the window motors, and so I thought about some kind of a little device that would add Wi-Fi support and a microcontroller directly inside the little device. Now, I really wish I had one here that I could show you. I don't think I do, because they're probably all installed on installed on the Windows. But the motors themselves are quite long, and they have a battery compartment in them. The idea is that it can run off batteries so that you can simply mechanically mount it to the window and then use infrared to control it without any external wiring, or you can run wiring to it to do LIN bus control and pass power down that same cable. Now, because I've cabled it with LIN, I'm sending power down the cable, and I don't need the batteries. And in fact, the battery compartment is empty. So this little board, now if we're looking back at the screen, the actual purpose of this, and the reason that it's got these weird cutouts in it, is that this is designed to fit physically into the battery compartment of the window motor. And inside the battery, now I wonder if I can do this. So I'll just, let me see, I'll make a polygon on something. Yeah, so a AA battery is probably about that size approximately. I've just made a rectangle, and so what happens is that there are 4 of them that go in here. So there's one there, and then another one in series with it, and then one down here and another one in series with it. So a total of, I think it's 4 batteries. It might be 6, I can't remember actually. And then there are little plastic tabs that curve up. You know, this is one of those things that's very hard to explain unless you can physically see the actual device. Now what happens is that there is a plastic tab that curves up from the center line, and you can see these little marks here that I put on the document layer. These aren't printed or anything, this is just for my own visual reference as I'm laying out the design. That's the exact center line of the battery compartment, and there is a bit of plastic that comes up directly from that center line, and then it curves down and wraps over the top of the bottom row of batteries in order to hold it clipped in place. So the objective with this design, and I know in the past I've been starting by demonstrating the schematic before I show the mechanical side of it, but in this case the interesting part is the mechanicals. So what I've got in the middle here is an ESP-12 module, so ESP-8266. That's sitting right in the middle of the battery compartment, and it's spaced in between the 2 plastic tabs. Now the idea is that this board, and I forgot to mention, I haven't actually fabricated this board. I designed this quite a while ago, and I haven't actually had any of them made because I was going to cover this in a future Superhouse video, and I might as well do that as all part of the process. But the idea is that what it does is connects in down here to get power in. In fact, let's switch back to the schematic layout and we'll have a look in here. So we've got a power input, so we've got ground and 12 volts, because there's 12 volts that's sent down the wire from the LIN bus interface, and it then goes into an onboard regulator module. Now this is something that I'm going to change about this design, and in fact there's another version of this design that you'll see in just a second as well. This regulator module is one of those little cheapy boards that you get from AliExpress or whatever. It's this one is the 4-pin version. You can also get it in an 8-pin version. It's basically a little rectangle with pads, and you solder voltage in on one side, you get voltage out on the other. And what I found in testing is that they are rubbish. So I started off by designing it around these little modules because they're cheap. You just drop this in, and because it's switch mode, it means you can take 12 volts in, get 3.3 or 5 volts output, and it's reasonably efficient. But I just found that the quality of the voltage that comes out of it is really bad. It's quite noisy, and also the modules tend to fail. So I designed these into a couple of projects early on and then revised them, and there are projects coming up where I've switched these out for other things. So for now, this has got the design of that regulator module in it, and that just gives 3.3 volts out, and then that 3.3 volts comes down to it controls the ESP-8266, which has got the usual reset and reflash switches on it, because you need to put it into the right boot mode. So if you look at these, there's the CHPD and the reset, both have biases on them to pull them high. You can see that GPIO15 has a bias resistor to pull it low, and GPIO2 biased high, and this is biased high on GPIO0, and then when you press the button it pulls it low. So that then, and by pulling it low, it also turns on the LED, so you can see when it's in reflash mode. So that's this whole part of the circuit right there is basically, in fact, yeah, right there is basically a bog standard ESP-0266 schematic with the supporting parts necessary to make it boot into the right mode. So that little block of design is something that is repeated in lots of projects. That's very common. And the ESP-8266 then talks to using serial comms to the MCP-2003. Now this is it's a converter chip. What it does is take regular TTL level serial communications and it converts it to LIN bus compliant serial communications on the other side. Basically you just take serial on one side, LIN on the other, stick this chip in the middle, and hey presto, you've got bidirectional communications. It's pretty cool. That is the same chip that I use to control my blinds at the moment. But at the moment what I have is that chip built into a system that is just near the switchboard, and then I've got cabling running all the way to the motor. And what this does is move the controller and take all of the control logic, which I currently have remote, and move it inside the motor and mount it inside the battery compartment. So we then have this little header over here. So there's not really a lot that you need to know about this. It just needs a couple of things like the wake pin you need to pull low, bias low so that it's awake and operating. CS is chip select so that you can have multiple interfaces and then you can select them. In this case we've only got one, so I've biased it high. So it's always selected, and as long as you apply those, you just talk to it using serial comms, and that's all very easy. So what we have then is this connector, which gives us ground data and 12 volts, and this is where the connection goes out to the existing onboard controller, because the idea is that the PCB that's inside the window controller is still there. It's just that, let's get rid of that. It's just that we now have a little Wi-Fi enabled device mounted inside the battery compartment that can send commands to it. So now that you've seen the schematic and we've come back to the hardware, this might make a little bit more sense. So we've got the 12 volts input that I showed here. So the idea is that my existing cabling would only supply power. There'd be no communications over it. It wouldn't need to. So power would come in on these screw terminals and go all the way across the board, and this layout is dictated essentially by the physical constraints of having to fit within the battery compartment. So there's a smoothing cap there, and then this 12 volt rail comes all the way through and it goes to the input of the voltage regulator, which is over here, and then we get 3.3 volts out, which comes down to this little serial header, like FTDI header, so that I can do reflashing, and also supplies the ESP-12 module. So there's a big capacitor right there for a bit of bulk capacitance, not too far from the input on the ESP-8266. Because one thing that you can find is that ESP-8266s are very susceptible to variations in their supply voltage. It doesn't take much of a sag or variation in it or electrical noise for the 8266 to spontaneously reset. So if you're having problems with ESP-8266s resetting when they try to connect to Wi-Fi, for example, because that causes a really big current surge, maybe a few hundred milliamps, putting a big capacitor right near the 3 volt pin can be a really good idea. So supply comes through to the ESP-8266, and then that has serial communications coming over to the interface chip over here. So this is the chip that does the regular serial to LIN bus conversion, and the LIN bus output, so the data line, comes out of that chip and down to here, and then we've got a little three-way header. At the moment this is just like a 3 solder points. It's like a 0.1 inch pitch that I just stuck down there as like a generic way to connect. And that's got the 12 volts available on it, it's got ground on it, and it's got data on it. So the idea is that the way to install this inside the window motor is to take the cover off the motor, pop this into the battery compartment, you run 12 volts into the screw terminals, and then you have a little cable which would be just 12 volts data and ground, which would loop around to the input on the onboard controller. So the existing controller would just continue doing exactly what it's doing, and it doesn't need to know any different. As far as it's concerned, it's got some external device connected to it, supplying power and talking LIN bus to it. It doesn't know that that device happens to be jammed inside its own battery compartment and connected to Wi-Fi. So that's kind of a cool little project. I quite enjoyed laying this one out just because I had to work within the physical constraints of where everything goes. So let's have a look at the control panel, next one down, and I'll jump straight into this because it's a direct continuation. Save? No, I don't want to save the other one. Yes. So now that you've seen the other one, this will look super familiar because it's basically the same thing. The only difference is that it uses an ESP-01 module instead of the ESP-12 module. So if we go back to the schematic, you'll see it's got the same voltage regulator input. It's got the ESP1 here instead of the ESP8266, but apart from that, it's got all the same stuff for the BIOS light pins and the reflash and reset buttons. And then it's got serial communications, so all this part of the circuit is exactly the same with the MCP2003 LIN interface chip. Now the reason for that is I've got hundreds of ESP-01s, and I've been looking for a project to use them up. It's one of those things where I can't stand them being wasted. I ended up buying them. I've used them in many projects over the years, and they're very limited because of their very small amount of I/O, and also they typically have a very small amount of flash, so you can't store a whole lot of code in them. But and I know they're only worth like $1.50 or something each, but I can't stand to throw them out. And I can't stand to see them just sitting on the shelf in a box, not being used for anything. So I laid out this particular board in a way to use that up. And because of the spacing, I had to put the module over here and then the regulator over here. So I don't know which one I'll end up fabricating, which PCB. There are limitations with ESP-01, so I might just fabricate it for the ESP-12, but I don't know. We'll see. That's a project that I need to get back to. It's one of those situations where I did the layout and then never really followed up on doing it. And a lot of this is me just sitting in front of the TV at night with my laptop laying out boards for the fun of it. So anytime that I get a chance, I'm in laying out a board for no particular reason, just because I want to. So we'll move on to this module. Excuse me. Don't think I've got any tissues around here. Now this is a really old project. It's from 2011 and it's an accelerometer module. So this is basically a little MEMS device that is a 3-axis accelerometer with analog outputs. Now a lot of accelerometers use I2C or SPI or some other communications method. This particular device, the MMA7361, is 3-axis, so it's got X, Y, and Z axes, and it just provides an analog output, which means that you don't need really any smarts in your microcontroller to communicate with it. all you do is connect these up to analog inputs on your microcontroller, and then you just do an analog read, and you got the value for the accelerometer. Now, obviously, that is going to severely limit the resolution that you can get, because if you connect it to, say, an Arduino with an ATmega 328 on it, it's only got 10-bit ADCs. So you can only get 10-bit resolution, which is not really a whole lot. So if you want accuracy, it's probably better to use an accelerometer with I2C or some other interface on it that can do better than 10-bit accuracy. But for simplicity and not requiring any code overhead in your project, this sort of thing is pretty cool. This module is very small. As I said right at the start of the first video where I was beginning my tour through the projects, a lot of these are going to be quite trivial, and this is one of the trivial ones. So it's just got an onboard voltage regulator, the MCP-1700, which is a very common little 3-pin regulator, and the module itself has a 0G detect output, self-test output. It's got sleep, so you can put it to sleep, but that's just pulled high by default. And the 0G detect is actually kind of interesting. I've never had to use this in a project, but the idea of it just intrigues me. 0G detect is like if you had a device and it needed to know when it was falling, what happens is that the accelerometer itself has the ability internally to detect when all 3 axes go to 0 acceleration or close to it. And 0 acceleration essentially means that it's falling. Now you might think, oh yeah, that means it's accelerating down. But in terms of gravity, it's actually not accelerating in any particular direction. It's kind of hard to explain. But basically, if you have an accelerometer that is at rest, just sitting on your bench, the force due to gravity going down through the x-axis will show a force equivalent to the acceleration of 9.9 meters per second squared, even though it's not moving. But if you drop it, because it is accelerating at the same rate that gravity is acting on it, essentially you have zero acceleration, and you get a 0 value coming out of the x-axis. Sounds counterintuitive, but once you understand more of the physics of how it works, that actually does make sense. So with the 0G detect output, what you can do is have, say, a microcontroller with an interrupt pin, which is reading from the 0G output from the accelerometer, and you could have a system that goes to sleep. Now, I'm totally making up an application here. Say you wanted to make a system that was that detected when your quadcopter was falling out of the sky, and it deployed a parachute automatically. What you could do is have a system with a microcontroller, which is normally asleep, so it's using almost no power, but it has an interrupt that is connected to the 0G detect output from the accelerometer. Now, most of the time, there'll be different forces applied. So if the quadcopter is hovering, you'll have vertical, x-axis force equivalent to gravity. The only time that the 0G detect output will be triggered is if it is literally falling at the rate dictated by gravity. So what you could do is then, when that output is triggered, the microcontroller wakes up and it does something like fire a solenoid and release a parachute. So one place that this is used is inside hard disks. If you have a laptop with a hard disk in it, like a spinning disk, not an SSD, sharp shocks against it when the disk is spinning and the heads are just above the disk surface can do incredible damage. So they can really stuff things up. So if you have a laptop, any reasonably modern laptop will do this, and I think it might even be built into the hard disks. If you take your laptop and drop it, don't do that, but if you do, what will happen is that it will detect zero gravity or zero G, and in the time it takes for the laptop to fall and hit whatever surface it is below it, it will move the heads off away from the platters and park them in a safe position, and it will try to stop the platters from spinning. So it'll spin them down or break them, as in not breaking, destroying, but breaking as in applying the brakes to stop them from spinning, so that by the time it hits whatever surface it lands on, the hard disk is in as safe a condition as it can possibly be. So zero G detection is used in that sort of application. Okay, and it's got a couple of ranges. There is hey, I didn't think I could talk for so long about a simple little breakout. So there is this little solder jumper, and let's jump over to the board, and it's got a whole lot of stuff in it. Let's turn off some layers. We'll get rid of the names, because that just makes things visually confusing. So so there's this little solder jumper here. So it says 6G. This just changes the full scale reading, because the outputs for X, Y, and Z, or Z axes, will go from 0G up to some level. And so what you can do is change if you have a smaller scale, you get better resolution for small movements. If you have a larger scale, you can detect much more rapid acceleration. So if, for example, you wanted to stick this inside like a rocket and measure the acceleration as it takes off, you would want a wider scale but less resolution. So in that case, you can bridge across your solder jumper, and it goes to 6G on full scale instead of 1.5G. Okay, I think that's probably all for that one. I'll just have a quick look at some questions. So, Andy Dick says, with your house switchboards, do you have one circuit breaker and one relay for every load you want to control? How many loads and circuits do you have in the whole house? Okay, good question. The way it works is that I have one relay for every load I want to control, but But I don't have one circuit breaker for everything I want to control. The circuit breakers are still grouped in a sensible way within the switchboard, so that I should have set myself up to do diagrams. So that if, for example, I've got 10 lights in a particular area of the house, there will be one circuit breaker which then feeds all of the relays for those lights as a group. This is the same basic structure that is used in regular house wiring, where you might have a couple of lighting circuits, a couple of power circuits, and that circuit will feed all of the lights in a particular area. And it allows you to have the minimum number of circuit breakers, but still have a bit of granularity. So you don't, if you trip a circuit breaker for some lights in one part of the house, for example, you don't take out the entire house. So there's a master circuit breaker and then sub-circuit breakers. So in my switchboard, I can't actually remember how many there are. I've got probably 40 outputs, I think somewhere in that region, 40 like different control outputs in one of the automation switchboards, and somewhat less in the other. It's like 20, and a few circuit breakers in each. So the output loads are grouped depending on where in the house they are and the type of load. Like lights, a group of lights will be on one circuit breaker, a group of power points will be on another circuit breaker, and so on. So next question is, I want to know how accurate is your PNP machine in terms of the pitch. So PNP is my pick and place machine, and it's, well, there are a couple of things. There is accuracy, there's repeatability, there is run out, there are a number of things that come into play here. I'd like to be able to just give you a number and say it's accurate to 0.1 of a millimeter or some fixed figure like that. But what I found is that it varies a little bit depending on things like whether the parts are rotated, because the pickup heads are not necessarily perfectly concentric on the little steppers that do the rotation for the, well, it's not Z-axis, it's for the part rotation. So it picks a part up and then rotates it to the correct orientation to put it down. And one thing I found last time I was using the machine is that when all of the parts are aligned in the tape, they're all side by side. If you pick the parts up and simply relocate them and then put them down in the same orientation versus pick the part up and rotate it and put it down in some other orientation, sometimes it can be offset a little. Now that sort of thing can be corrected for using an upward looking camera, which I don't have running right now. I have the camera, in fact the camera for it is this one right here, which I'm temporarily using to do downward looking stuff on my bench. The idea is that that's going to be installed in the pick and place machine looking up, so that OpenPNP can move the part over the camera and then it can do correction for alignment, and then it should become more accurate because it'll allow for offsets and things. So if it picks up a part and it's not quite centered, when it rotates the part will sort of move sideways. So in terms of accuracy, as I'm driving it around using the downward looking camera and the crosshairs, I'm normally positioning it in, well, you can position it in multiple steps depending on how coarse you want to be. Once I'm setting actual position for a part, I'm normally using 1/10 of a millimeter steps. So it's certainly good enough for 0603 parts, probably good enough for 0402, and I don't know that I would go smaller than that. 0603 parts, easy, basically. 0402 parts, yeah, you can do that. It's with 0603, it's quite rare to get a misplacement because those are big enough that it can handle it without too much trouble. Okay, so Pop Rock just asked, can you show us the pick and place machine? I missed that. I haven't shown that on a video for quite a long time. I'm just wondering about, okay, just for a second, I'm not really going to be able to get the camera very close, but let's see what we can do. I'm going to switch to a different camera, that one, and I'll be able to give you a better look at this some other time, but whoops, camera moved. So that is the basic machine. It's got some random stuff sitting on it at the moment, so you can't really see how it's set up when it's in use. Now I'll just move a couple of things out of the way. There's some AT-Megas in trays. Those are the trays that go into a pick and place machine for being applied. Random schematics and some little magnets that I've got. One of the recent changes that I made was I put down this metal base. So this is the frame from an XYZ carve, which is an X-carve knockoff. And then it's just got a head on it with a little nozzle. These are, which ones are these? These are Juki nozzles. This is a Juki nozzle holder. So it's got little retention pins in it. And the idea is that this mounts onto the hollow shaft stepper, which is just here. And there's a vacuum tube, so the vacuum passes right through the stepper motor down to the pickup head, and the pickup head can then take parts out of the tape and put it down on a PCB. So I'm not going to go into that in more detail now because I'm probably going to do a whole lot about that later on. Not in this video, but some other video in the future. So for now, back to here. So Tim C says, hi, greetings from the UK. Hey, I was actually born in London, and I haven't been back there since I was a little baby, but maybe one day I will get back to the UK. He says, are you still using 12-volt motion detectors for your presence detection? Yes. So I've experimented with a lot of different things for presence detection, and that's something else I want to cover in the future. I've also been using the Happy Bubbles Tech BLE beacon method, and just for at a really gross level to figure out if someone is home, for example, I've been using the Network Health plugin in OpenHAB, which tells you whether particular devices are on the network. So if someone comes home and they've got their phone in their pocket, their phone connects to Wi-Fi, it's now on the network, we can see their MAC address, and so we know that they're home. So at a very gross level, you can see, oh yeah, these people are home based on the devices that are present. And then I use security system motion detectors, which are powered by 12 volts, to do things like detect when someone walks into a room. So I can turn lights on and off and that sort of thing. And Happy Bubbles for trying to locate objects and people within the house. So I've got all the gear here to do a video about that. And there are some other things as well, but I won't get into that too much. Now, last night I was chatting to Unexpected Maker on Twitter, and I said, I'm going to do a live stream and try to keep it focused, and he said, no, you're going to end up going off on all sorts of tangents, and that's exactly what's happening. So let's get back to going through some of these projects. Now, there are 3 boards here which I'm not going to open right now, even though they are probably some of the most interesting boards, interesting projects in this whole thing. The reason is that these are the boards for ArduSat, which was the Arduino-based satellite that I worked on a couple of years ago. And the designs that I did for ArduSat itself have some legal issues in terms of releasing them with ITAR, which is the International Traffic in Arms Regulations. So what I'm going to do is not show you these specific boards, but I've since done other boards derived from them that were not sent into space, and I've got those under the name of LibreSat, so they will be down in the L section of the projects, and we'll get to those. Alright, Baro, this is another tiny little trivial thing. I'll spend like 1 minute on this, maybe. So this is a breakout for a barometric pressure sensor module. Once again, it's one of these simple little devices that you apply power to, talk to, and it gives you some information. Got to switch the camera back over to there. And David Watts is here as well. So, hey David, and hey Sion. So this device, we have same thing as before, which I showed you with the accelerometer. It's got the MCP-1700 as the little voltage regulator, so we just get power in. It's got I2C jumpers, it's got level shifters on here, level shifters. Should I get into this? I2C level shifting. Yeah, okay, what the hell. I'll give a very brief explanation now, and I might give a more detailed explanation later. So, I really need to draw diagrams for this. Thinking about this. All right, I'll give the dodgy explanation now, and I'll do a more prepared, better explanation later. So, I2C. You've probably seen I2C for many different devices, and it uses a clock line and a data line. And what happens is that you have a master device which will communicate with other devices that are on the bus, and you can have multiple slave devices, each with its own address. So when the master wants to talk to a particular device, it sends out a message with the address of the device, And when you're setting up I2C devices in your project, this is why you need to specify the address, which is usually like a little hex value. Because when the device, like your Arduino or whatever, sends out the message to talk to the device, it says, I'm looking for the device at this address. And then it gets a response. But the thing is that I2C needs to be able to support multiple slave devices simultaneously. So normally if you have two devices that are talking to each other, you can have, say, just a transmit line and a receive line, and it doesn't matter if they are constantly being asserted. The problem is with something like I2C, which is a multi-device bus, you need to be able to leave the bus floating, or any of the devices need to leave it floating when they're not actually sending anything. So basically they need to go high impedance and their output just releases the bus and it's still reading from it, so it's watching the voltage level, but it's not trying to change the voltage level because some other device on the bus might be trying to change the voltage level and send a message. So the way they do that is the bus is pulled up to a certain voltage by default, and then to assert the bus, each of the devices will pull it low. And so if you want to send some data, what you do is you release the bus to make it go high voltage, and then you assert it, you ground it to make it go low voltage. Now when you release the bus, the voltage normally would just float around. There's nothing to force it to go to any one particular level. So and this is why I2C buses have pull-up resistors. So if we look here, we've got the SDA. So this is the data line for the I2C bus, and there is a 4K7 pull-up resistor right here. And that comes up through this little cut track jumper, and it goes up to the supply voltage in this case. So what we've got is a line that if none of the devices on the bus attempt to force it to a different voltage, it will always try to be at the voltage that it's pulled to by this resistor. So if it's connected up to a 3.3 volt voltage rail, then it'll try to be at 3.3 volts. So what you can do is have devices that look for when the bus floats up with the resistor, or it's pulled down by one of the devices. Okay, so that is the general way that the multi-device part of it works. And that's what allows you to have multiple I2C devices all on the same bus. But the thing is, what voltage do these pull-up resistors take it to? Now typically what you would do is if you had, say, a 5 volt microcontroller and a 5 volt device, you would pull the bus up to 5 volts, obviously, because you want it to be either 5 volts or 0 volts or close to it in both directions to show a logical, like a logical 0 and a logical 1. So that is fine if both of your devices are on the same voltage level, but sometimes you have, say, a 5 volt microcontroller and a 3.3 volt sensor, say like a MEMS device that will only talk at 3.3 volts. So what you need to be able to do is adjust the voltage levels. So on the microcontroller side, you might want the bus pulled up to 5 volts to show that it's not being asserted, and on the sensor side you want it pulled up to 3.3 volts to show it's not being asserted. Now both of them will drop to 0 volts when one of the devices is talking. But what you really want is a little bridge that takes 5 volts in one side, 3.3 volts out the other. And it allows it to be pulled to 0 volts in both cases. And that is what I2C level shifting does. Now, and that's what this little circuit is about. Now, if this was designed to work with two matching voltage devices, this wire here would just come straight through. So this is the clock line, and it would come all the way through to this side. Here's the clock line, we follow it along, there's SCL, comes up to here, and it comes into the clock pin on the device, which in this case is a barometric pressure sensor. But it doesn't. Right in here in both the clock line and the data line, we have these MOSFETs sitting in the middle. Now, what happens with these is that the MOSFET itself has a like a bleed diode across it. This little Zener. So when you look at a MOSFET, you'll see that it has in the symbol, it's got the little Zener in it, and that's because this is actually within the structure of the MOSFET itself. And what we've got is, on one side of the MOSFET, they are pulled up to 1 voltage by these pull-up resistors. And in this case, it's pulled up to the supply voltage of the microcontroller that's going to be connected to whatever this little module is. So on this side, if the microcontroller is not asserting the line, so this is just left floating, it will be pulled up by the 4K7 resistor to the microcontroller supply voltage. Now, over on this side of the MOSFET, we've also got a pull-up, which is going, in this case, to 3.3 volts. So that is the supply voltage of the device. So that's of the sensor. So if you look at these two halves, we see this side of it is at 5 volts. This side of it is at 3.3 volts. And the way this MOSFET is set up, basically this is providing a, when it turns on, it's going to force the level down in both directions. And this is where I need to look up the data sheets. It's a long time since I've worked on this. When was this? 2014. So the MOSFET itself, when it turns on, which will happen if either side of it is pulled low. So if, for example, the sensor down here tries to pull the clock line low, it pulls it down to 0 volts, which it can do because the pull-up is only through a 10K resistor. That will then cause the MOSFET to, I can't remember which way around this goes. I'm going to have to look this up before I do a better explanation of this part of it. The upshot of all of this is that the MOSFET turns on in order to assert this line. That was rubbish. Okay, I'm going to look that up. And what happens is that when this line is low, is asserted low, this line will be low, and when this line is asserted low, this line will be low. So it's like a bidirectional, in either direction you can pull a line low and the equivalent line on the other side will also go low. So we achieve the result that we wanted of either device being able to assert 0 volts. But when neither side is being asserted, they both float to the higher voltage that is dictated by these pull-up resistors. So in this case, on this device side, it'll be pulled up to the 3.3 volt, and on this side, it'll be pulled up to the 5 volt rail. So what that gives us is the ability to run this little device. Now, if we look at the note up here, it says sensor supply voltage 1.5 to 3.6 volts. So this is, once again, a MEMS-based device, and it's an I2C barometric pressure sensor that runs up to 3.6 volts. So what we're doing is we're supplying it with 3.3 volts off the regulator, but down here it says operating voltage 2.3 to 6.3 volts. The reason for that is that we can only go down to 2.3 because we lose a little bit on this regulator. So we've got 0.18 volt drop and up to 0.3 volt voltage drop. So we can run this little module and I'll switch back to it, at up to 6 volts. So we could connect this to a microcontroller running at 6 volts if we wanted to, and it would work just fine, even though the sensor is only designed to operate at up to 3.6 volts. Because the onboard voltage regulator takes care of supplying the correct voltage to the sensor, and those little level shifting MOSFETs take care of making sure that the voltage that is exposed to the sensor is no more than it can handle. How is it that I can talk for like 15 minutes on a breakout that is only a few parts? This is ridiculous. Okay, Baro. B-card light. Oh, this is a kind of cool one. This is a SuperHouse business card, but as a PCB. So there are some questions, but I'll get back to those in just a moment. Oh, hang on. Okay, before I go on, Robert Diamond has a very concise explanation there for the level shifting. It says the MOSFET is off normally because voltage source equals gate voltage. No, source voltage equals gate voltage. When the device pulls it low, VGS hits 3.3 and the transistor turns on. Yes. So that is the explanation that I was trying to fudge out of my brain earlier. And so one of the critical things when choosing those parts actually is that the VGS value for the MOSFET needs to be small enough that it will actually turn on at the critical time. So you can't do that trick with all MOSFETs. You need one with a spec that has a VGS value that is low enough that the threshold works. So okay, so back to this one. We've got, this is a fairly simple one, but it's once again interesting from a physical or mechanical point of view. So we've got the ICSP header here, standard thing that you would expect, and then over here we've got a USB connector. This is just like a 6-pin micro USB, and it's got voltage protection. These are little TVS things. They're like 2 Zenas back to back, and they do voltage clamping. Then we've got some power supply smoothing. I'll skip over this middle bit for now because we'll get back to that in just a second. And over here we've got an ATtiny 85, and this is a surface mount package AT25. ATtiny 85. And then I've got a button. Because we've got so few pins available on the ATtiny, I've got a couple of them doubled up. For example, the MOSI pin, which is used for programming and SPI, is also being used for a button in this case. So what I've got is, normally the button is open circuit obviously, and what you can do in the code running on the ATtiny is that when it starts up, it can pull the internal pull-up resistor on so that this input PB0 goes high, and then when you press the button it's pulled low, so it can detect that the button has been pressed. And in a similar way, the MISO line comes out, it's used for programming, but it also goes through this current limiting resistor and an LED. So the LED just shows that something is happening. So as you can see, we've got a start-stop button and a recording button. So it does something when you press the button, starts recording it. Over here we have a TMT6000, which is a visible light sensor. You've probably seen things like LDRs or light-dependent resistors, and those are okay, but they tend to be a bit crude. They're not very well calibrated typically or repeatable. The TMT6000 is a little light sensor. In fact, there's a breakout for that as well, which is much lower down. It's in the L section, and it is optimized for reacting in a linear way that matches the human response to light levels, because the human eye is not necessarily like a well-calibrated machine. It has a bit of an unusual reaction to it in terms of how bright you perceive things to be. Once you get above a certain level, you get diminishing changes, etc. So the TEMT6000 is a light sensor which gives you a very quick and reasonably accurate representation of what the human eye would perceive in terms of the brightness. So it's kind of cool as a little light sensing device. And it's a phototransistor. So it's basically if you look at a normal transistor, you've got a base, a collector, and an emitter. And in this case, there is no base pin, it's just got a collector and an emitter. So the base is the light level, and just in here, the more light that comes in, the more it turns on the transistor, and then the output changes. So it's just running in a little voltage divider thing here, essentially. There's a 10K pull down, and then connected to the emitter of the transistor and the resistor. We've got this line which comes along to here, and it goes into PB2, which is one of the inputs on the AT-Tiny. So what that allows us to do is sense light. Okay, so if you're just looking at this circuit in isolation, it's a reasonably straightforward light sensor circuit with a microcontroller and a USB interface. And what you can do with the AT-Tiny is that there are libraries that allow you to do serial communications through just using a couple of the regular pins. So you don't need like an FTDI chip or anything like that to do the conversion. What I've done here is I've got 68 ohm resistors just for isolation, and there are the data pins coming out of the AT-Tiny through the resistors, and then there are some that's connected to the data lines on the USB socket. So by running the right software in the AT-Tiny, we can communicate by USB directly. So yeah, if you look at this circuit in isolation, you would say, oh yeah, that's just a fairly straightforward data logging sort of thing, or it can read from the sensor and report by USB. The interesting thing here is it's in the form of a business card. So I'll just turn off some layers. What will I turn off? T-place. I'll turn off both those layers. And what I tried to do for visual reasons, aesthetic reasons, was route the entire board on one side. So if we come over here, in fact I'll turn on vias, and you'll see there isn't a single via in the entire place. And turn on T-docu so you can see where all of the parts are. So I did a fair bit of fiddling around with this, trying to, before I actually did the routing of the tracks, I moved all the parts around, trying to make sure that I could route everything with no vias, because I wanted 100% of this design to be on one side of the board, to leave the other side of the board totally clean. I didn't want there to be any holes or obstructions to it, so it's just pure copper on the back side of the board. And I also designed for the ICSP header, these are pads that don't have holes in them. So they're just little round pads. And in fact, I will grab one of these and show you the real thing, so you know what I'm talking about. It's easier to show than it is to business card. There it is. Oh, that's empty. B card. Where? I really need to do more preparation for these and get the devices out so I can show you the real thing. I actually have one of these in my wallet somewhere, which is not in the room. I really do want to show this one to you. So I know it's going to mean you sitting there waiting for me. Oh, I might have one in the drawer if I'm really lucky, because I know where I have one of these, but it's off in a different room. So I would have to leave you just staring at an empty room while I go to get it. Oh no, very good. Got one here, got a few here. Now I'm going to switch to the overhead thing. And this is the design. So I'll show you the other side first. Now if you, it's actually kind of hard to see because the solder mask covers all the tracks. But if you get the angle just right, you can see that there are tracks there, like just running up here all the way around in a big loop. And if I temporarily switch back to the iMac desktop, which is Eagle, you can see here that's the big track that comes up around this area. And up here is the light sensor, so that's the TMT 6000 right there, and USB socket on the side. There's the AT Tiny, there's one of the buttons over here, and I tried to make it visually, visually symmetrical as well. I need to turn on the T-Origins layer so we can select things and see them. So we've got the light sensor up here, and then down here symmetrical, so it's the same distance, I think. Oh, not quite. It's got the button, and yeah, I tried to put these in the same place. For example, you can see that there's this LED down here, and there's this one up here. So where are we? There. So these LEDs are symmetrical about the axis, and I kept everything here on the center line. So the result, if I switch back to the little thing again, is a PCB which is the size of a business card, and it's all single-sided. So if the parts are placed on here, in fact I do have one of these with the parts on it, this is just a blank board. It is a USB enabled light sensitive data logger, but as a business card. And because, well, you can see here that there are holes drilled through because of the socket. The USB socket fits on here, and it's got holes for little mounting lugs to make it stronger. That's the only break in the copper on this side of the board. The rest of this copper is just totally smooth. So that was, and also you can see it's very, you may not be able to see on the camera, it's a bit hard to see, but it's very, very thin. I think this was 0.8 millimeter PCB material, might have been 0.6, I think it was 0.8. But even though it's so thin, it's still quite rigid because there's unbroken copper on the back, and most of the front is also unbroken copper apart from these tracks. It's still quite rigid, and so even though it's almost as thin as a cardboard business card, but it's a PCB. So yeah, okay, let's have a quick look at any questions. No, nothing much. Injecting caffeine stat, yes, I know that feeling. Don't think there's a whole lot more interesting about this design. So yeah, it's just The artwork that's on it is printed on the PCB. It's just like having a business card made, except that you have it done through a PCB factory instead of through Officeworks. Costs a little bit. They're kind of expensive business cards, but oh well. It was a fun little project. So, B-Card Lite. The reason I put that on it was I was going to do different versions, and that was with a light sensor, and I wanted something else as well. Okay, beacon. This is, the name is a bit strange. The idea was that it was an infrared and RF beacon to be able to transmit things like an IR blaster style project. And this one, what was this designed for? Let's just go back to the schematic before we look at the board. Okay, so this was designed for a spark core or a particle photon or you know, those sorts of things. It's that footprint. And the design is reasonably simple. The idea is that, well, the spark core, if you don't know, is a little, in fact I'll grab one and show you. It's a little microcontroller module, and I think I have a whole bunch of them here somewhere. Thought I did. Maybe not. I know I do have a couple of hundred of them sitting around in a box somewhere. But right now, I'm not sure where they are. But it's a little microcontroller module that has Wi-Fi in it. And one thing that I really like about the system, in fact, what I'm going to do is show you a little of how this works. Build. Okay, so the spark core looks like this. So this is, well, like this. Little module that you can plug in. It's in a DIP format, and it's got USB on it, so you can program it via USB. But the really cool thing about them is that they have this whole software ecosystem around them that allows you to manage them using over-the-air updates. So let's see, if I log into the interface on here, so this is the build environment for it. It's all an online thing, which I don't normally like, but in this particular case it works well. What you can do is go into your list of devices. So if I click on my device list here, I've got cores. So down on the left you can see all of the Spark cores, and you can see one here that's online, Core 59, and then photons, and you can see a few there that are reporting themselves as online. And you can then manage them remotely. So if, for example, I wanted to reflash a device, what I can do is set this as my target. I can specify what version of the firmware I want to be on it. I can make the LEDs on it flash, so if I've got dozens or hundreds of the devices, which I do, you can make it flash to indicate that, yes, that's the one you're talking to. And then in your code, what you can do is say, I'll just pick blink. You can then say, you can flash it basically, and it will push. So I won't actually do this, but if I clicked on flash, what it would do is compile this program, and the little device, which is out there somewhere, it could be anywhere in the world, it's connected to Wi-Fi, and it's expecting updates. It's running whatever program it currently has installed on it, but just by clicking flash on here, it'll be compiled, uploaded to the distribution system that Particle run, and then that little device will download the new sketch and will run it, and you can do updates. So if you are managing, and there's also a dashboard as part of this. So what you can do is have classes of device, and you can say create a new piece of firmware and then push an update to all of the devices of that particular class. So if you're making a product and you want to be able to do firmware updates for thousands of customers, and this gives you the dashboard to be able to manage fleets of devices and onboarding and all of those sorts of things. So I ended up using Spark cores a few years ago for a blind controller project, and there were a lot of them distributed around the place, and a lot of them are still in use. And then particle photons, when the photon came out, we ended up ditching that project because the photon had some problems that the core didn't. We found that the core was super reliable and didn't have any issues with power supply fluctuations or anything. But then when the Spark company renamed itself to Particle, and the Spark core was dropped and replaced by the Particle Photon, which had a different processor and a different design, it's in theory a drop-in replacement, but it's actually a totally different architecture. And we found that even slight variation, like little variations in the power supply, would cause it to spontaneously reset. And also Wi-Fi would go deaf, which was horrible, because then you might have a device that was installed in a customer site and it's a long way away and it goes deaf and it needs to be power cycled. So we were constantly telling customers, turn it off and turn it back on again. And that's rubbish, you can't do that. So we ended up going away from particle photons for that reason. And that's why I've ended up with hundreds of particle photons, because we took back all of the devices and replaced them with a totally different device. And I then went through and harvested parts out of all of the returned devices. So I've got little power supply modules and particle photons and things. So I've got a heap of them sitting in a box here, which I could use for projects. And I will do that one day. But to get back to this design, so what we're looking at here, that is the little self-contained Spark core, and the particle photon looks almost identical. And that, lead page, and that is what this footprint is for right here. So that's the footprint to put a Spark core or a particle photon on the board. It's got piezo on it. Now it looks a bit strange because I've got two piezo footprints on here, and that is similar to what I was talking about in the last video with having two voltage regulators with footprints that are overlapping, so you can put in either type of voltage regulator. You don't fit them both, you only fit one. So one of these is a through hole and one's a surface mount piezo module, which you'll see in just a moment. There is some power supply decoupling here to try to smooth out the power supply. And over here we've got the interesting bits. So we have a 433 megahertz RF transmitter, and this is a little module. It's like an OOK module that you can use to transmit signals, and there is a 433 megahertz receiver and similar things. So this is basically the same as what you'd find in garage door remote controls and those sorts of things. And then there is an infrared transmitter with an IR LED. There's just an activity LED as well. And there is an IR receiver. So this is an infrared sensitive phototransistor. Same thing as actually in that last project where we had the voltage divider with the resistor at the bottom and the transistor at the top. And then depending on the received signal, in this case it's infrared, in that on the business card with a light sensor it was receiving visible light, but now it's receiving infrared. And then what we can do is take the junction of that divider and use that to detect infrared transmissions. So we can receive signals from an infrared appliance remote control and that sort of thing. So if you look at this design overall, just in the main building blocks, it's fairly simple. We've got the brain of the system here as the Spark core. It's got the ability to beep using piezos. It can transmit at 433 megahertz using this module. It can receive 433 megahertz signals using this module. It can transmit infrared using this IR LED, and it can receive infrared using this infrared sensitive phototransistor. And the idea with this project was that it would just be a little universal Wi-Fi to IR and RF bridge. So what we could do is have it receive signals. You could make it learn a signal from a remote control by receiving it, either the 433 megahertz or infrared. And then once it's learnt it, it can also then transmit it back out again. So if we look at the, I keep missing that. If we look at the board, it's a bit of an unusual shape, and I will show you why in a second. I'm pretty sure I can find this one physically. So looking at the major building blocks again, same as what we had before, we've got the particle photon or the spark core sitting right in the middle here, and it's aligned so that its USB socket matches the end of the PCB, so it will protrude through the case or be accessible through the case. And up here we have which is that one, the receiver, and that's the receiver module. Yes, so it's the 433 megahertz receiver, and then down here we've got the 433 megahertz transmitter. We also have the infrared infrared LED up here. So this is what it can use to transmit infrared signals, and the infrared phototransistor here. So this is what it can use to receive IR signals, and an activity LED, so that it can just show when it's doing anything. Now, IR beacon. I do have a box for this one somewhere fairly handy. Let me see what I can find. It's a while since I've worked on this project, so I'm pretty sure that I've got things fairly close by. Just in the other room, I think. So I've left you waiting for a while, and I didn't find the particular thing that I was looking for, but what I have found is the some of my particle photons and things. So I'll just chuck them under there, and so that's what a particle photon looks like, and this is what the spark core looks like, which is the original one. So the photon is technically, according to the specs, a better board, but we just found that we had reliability issues with that compared to the spark core. Now I'm sure I've got these little devices here somewhere. No, I just haven't been able to find them. So what I'm going to do instead is show you something similar for a project that we will get to a little bit down the track. So I won't show you this one in detail right now, but it's the same concept that the board is designed. In fact, it fits into the same physical case as this. So if we have a look at the board design, you can see the shape of it is quite strange. It's got those little cutouts on the corners, and over on the right side, over here, there is a little hole or a little semicircle. So if we look at a board for another project, so you can see it's a similar sort of shape. This one's ESP-0266 based, not SPARC core based. I'll chuck this over here on the document camera. And it's the same sort of thing. It's got these holes cut out of the edge. The connection is on the end. It's USB based on the IR device, but similar sort of concept. And the reason for that is I want it to be able to fit into a box like this. So it's just a project box. Oh, here's a 301. So it's a project box with little mounting slots on the side. So it's got there's a little notch cut out of it here. And so what you can do is put boards in it just by popping it in and out. Makes it really easy. So you can see it's got the little retention notch in there, and it means you don't even need any screws. Basically, you just put the board in place, push it down, and it clips in. That's it. It's all securely held. And on the design for that little IR and RF beacon, what you would have is the particle photon in the middle. In fact, I think it might have been a slightly bigger case. I can't remember. And then you have the three devices here: the infrared transmitter, the activity LED, and then the receiver. But that's the general concept. It's not quite the same thing, but it shows you the thinking behind doing the design of the PCB in that way, with that strange shape. Now, where are we at in time? So I'm at an hour and a half. Let's see what projects I've got coming up. So that was the IR RF beacon. Yeah. Now this is a project that I would really like to cover in, like to do a dedicated episode about this, because this is a really handy little device. You can use it for things like controlling air conditioners that don't have any way of integrating with a home automation system. Because what you can do is use the IR libraries that are available for Arduino to send control signals, and you can control TVs, all sorts of stuff, garage remote, garage doors. So I'm going to do, I think, a whole video about this particular project because it's kind of handy and cool. Now, let's see how much further I should continue. Okay, what I'm going to do is cover the ESP-12 and then stop, because the next project that we get to after that, which is the brain, is actually a really significant project that will probably take a fair bit of explanation. That's the device that is the core of my whole home automation system. So I think that would be a good place to start the next episode, and then perhaps spend a bit more time on it. So for now, what I'm going to do is just show the ESP-12, and let's have a look at what's going on with this. So we've got the schematic, and I've got to keep remembering to switch my my view. So this is a breakout that puts an ESP-12 module, so it's got an ESP-8266 on it, into the correct format to plug into a Zigbee socket. So Zigbee or XBee is something that you see on quite a few projects. It's probably not as popular anymore. It used to be used in hobby projects a bit, and the little modules have a form factor that it's actually quite similar to that SPARC core and particle photon I was just showing you. So let's see if I can maintain my terrible track record of not being able to find anything that I want to show you. Oh, amazing. I've actually found it. So I get to show you the hardware. So with a with XP, let's start by looking at that. Oh, hang on. I'm actually telling you the wrong thing. I'm getting myself confused because this is not in XP format. I've got that as well. This one is in particle photon format, which actually makes it even more relevant to what we were just looking at. So let's switch around the order and look at the hardware before we look at the design. And that is the hardware. And now I'll just pull out one of these. So this is a Spark core that we were just looking at a moment ago. And it's got, as I said, USB and Wi-Fi, etc. And then this is the Core SP-12. Now, I mentioned previously that we had some problems when we transitioned from the Spark core to the particle photon, and the project became quite unreliable. One of the things that we experimented with, and when I say we, I mean myself and Angus Grattan, who now works at Espressif, and at the time he was working for me on this project. In fact, this is how he ended up, I think, indirectly at Espressif, because he was working on these ESP-0266 projects with me for a Superhouse. So this was commercial projects that Superhouse was doing, and we ended up doing a few things that resulted in him getting a job at Espressif. So this is intended to be a drop-in replacement for a Spark core, but with an ESP-8266 on board. So if you have a project that was using a Spark core previously, or a particle photon, you can unplug it, plug this into its place, and now you've got an ESP-8266 doing the same job. It's got an onboard voltage regulator, so you can feed 5 volts into this, and then the ESP-8266 runs at 3.3 volts. It's got the buttons on it for reset and program, so you can hold down the program button, press reset, and it puts it into reflashing mode. But the idea is that what you would do is load a basic sketch onto it initially through a physical interface, and after that you would use over-the-air updates. So that is meant to be a direct drop-in replacement for a particle photon or a Spark core. So looking at the design again, now that you know what the actual physical device is, this is the XP Pro. What is going on? I think I might be looking at the wrong project here. BSP. Yeah, I am looking at the wrong project. This one is the so the physical project I've just been showing you is not the one that I've got here. Here's the thing, it's confusing. It's been over the space of several years, and I've done a couple of these projects that are very similar in many ways. So there's a lot of overlap between them. So this particular project that I've got open, in fact what I'll do is let's have a look back at BSP-12. Yeah, that one I was just showing you was the Core SP-12. Let's go to this one instead. So we're jumping slightly out of order, but oh well. I'll just skip over this one next time, and then later I'll show you the other. So schematic for this, once again we do the dual footprint trick for the voltage regulators, and then over here we have the ESP-12 in the middle as the core of the whole thing, and then we have all of the standard things that we've seen many times before with the bias resistors that are required to set the ESP-8266 into the correct boot mode, and then we've got the reset button and the program button. So when the program button is pressed, that pulls GPIO 0 to ground, and then it goes into programming mode if you reset it while it's got that pulled low. When was this from? 2015. It's not that long ago. So then we have a couple of headers. We've got the two headers on here which replicate the Spark Core headers. So this sort of circuit is reasonably simple. If you ignore the power supply at the top, just look at the bit in the middle. What it really comes down to is ESP-8266 with the necessary bias and programming buttons and breakouts for the different I/O lines. Now, one of the limitations is because the ESP-8266 only has a single analog input, and it's a very restricted voltage range. It doesn't go up to 3.3 volts. What we've got here is only what does it? No, that's right. CHPD can be an analog input as well, I think. So what we've got is most of the analog inputs that are on the Spark Core header aren't actually connected. So you can't, it's not a 100% compatible drop-in replacement for a Spark Core or a particle photon because it doesn't have all of the pins to map to those headers, but it does most of them. And the digital pins over here are mapped through, and we do have some limited analog input. So we've got the single analog input here into the ADC is on A0, and then I just mapped these other two pins through onto A1 and A2 headers, even though they're not actually analog inputs. It just means that you can use them in the project if you want to. So if we go back to look at the board, it's not all that much interesting to learn here, and you've already seen the physical board. The only interesting thing, I suppose, is just that I had to squash this in. And if you look at an ESP-8266 module, you'll typically see that they have castellated edges, which is a topic I'll get into some other time, I think, and next time I'm doing an ESP-8266 project. And they also have very fine pitch through pins. The pads are on a 2mm center, not on 0.1 inch center, and the holes themselves are quite small. So what you can see here is that the footprint for the ESP-12 has these 2mm pitch through holes, and the castellated edges are just up here. So if you were mounting this module as a surface mount module, so putting it flat down on the PCB, what you would do is have surface mount pads just on the edges of the board here, right about there. So for each one of these there would be a little surface mount pad. But as you can see where my cursor is, there's no room because we need to fit within the physical constraints of the footprint of the, in this case, what was it, the Spark Core. So what I did was use the little 2mm pitch through hole pads on the ESP-12, and it just clears. You can see that one row of pads in here just fits inside that header, and the other row of pads just fits inside that header. And it's all pretty neat. It's tight, but it's neat. You can still solder onto the tops of these pads fairly well, and that works okay. So the result is that you end up with the module floating up above the carrier PCB instead of being hard down against it. So I'll switch back to the document camera, and now that you've seen that explanation, it'll probably make a bit more sense when you see this. In fact, what I'll do is show you. So this is how most people think of using something like an ESP-12 module. It's surface mounted directly down onto the PCB. So there are little surface mount pads on here. Is it focusing? Kind of. And it's soldered through on the edges of those castellated pads. But I didn't have the width to do that on this PCB. So what I did, in fact this one isn't even soldered on, so you can take it off and you can see. So you can see there that there are the rows of 2mm pitch through-hole pins, and then the module, the ESP-12 module, has these through holes, and it's actually very tight. So these are really small holes. This is a 2mm pitch header, so it's not the same as the regular header. And then by fitting this to the module, and then the module onto the PCB, it floats above the PCB because it's held up by the little plastic spaces, and it's electrically separated from these headers. There is a good safety margin there. It shouldn't short circuit or anything, but you end up with a fairly neat package. It just fits in, but in terms of the profile, it's higher than what you would expect normally from an ESP-8266 module. Ooh, I'll get the angle. Because it's not surface mounted. It's using the through-hole pins. And that gives us then a module that we can drop in as a replacement for a spark core or a particle photon. But now we have an ESP-8266 in its place. So that's another little board that I've never actually released. I designed that one, as you saw, on the date a few years ago. But in fact, when was the date? Because this was designed for a particular project, when was it? April 2015, so 3 and a bit years ago. It was designed for that commercial project, and I was intending to release it, but never got around to it. It's a bit of a strange crossover thing, because it was to fulfill a specific need where we had an existing project that was designed around the particle photon, and we wanted to replace it with an ESP-8266. So most of the time, if you were designing a project around the ESP-8266, then you just design it that way. It'll be optimized for the particular part, and like the footprint would be set up for it. But we already had all of this hardware in place that was set up, and what we were hoping was that we could just go through all of the existing boards and pop out the particle photon modules, pop in these Core SP-12 modules, and everything would be fine. So if you have that particular use case, this might be good. So I'm going to wrap it up here. I'm just going to have a quick look through some of these questions. So oh, there have been quite a few. Okay. So Bhavesh asks, can you do your toaster reflow oven controller? Yeah, I'll talk about that some other time. I won't do it right now. And, oh, hang on, or maybe that was replying to Unexpected Maker, who I think is, hang on, I haven't scrolled back far enough. All right. So, Unexpected Maker says, I'd like to know how you pick your parts for your boards. So many suppliers with same but different parts, so many choices, etc. Talking about stuff like LDO, VREDs, and UARTs and gyros, etc. Okay, so part of it is just familiarity. In a lot of cases, it ends up being just a matter of, hey, I've used this in another project and I already have the footprint in Eagle and I have parts sitting on the shelf, so I'm going to use that same one again. Even though it may not necessarily be the ideal if you're approaching it from a totally objective point of view, starting, greenfields. So a lot of it is inertia and habit, but then beyond that, it comes down to reading data sheets and looking at other example projects. So part of it is if there are existing projects out there that have software, for example, to talk to a particular type of sensor, that can be a really big thing. Say you've got an accelerometer that is on I2C and you don't want to have to implement a driver for it, and it's already done there in some example Arduino library, then use that. Makes it really easy. So a fair bit of it is that. So let's see, not MOSFET, injecting caffeine. Okay. Okay, so Duncan asks, why did you want a USB connected light sensitive business card? Just a gimmick, no real reason other than that. What I wanted to do was have a business card that I could give people, and it would make them really look at it and hang on to it and not just throw it in the bin. So I wanted something that had some purpose, and the idea is that when I give it to people, I give it to them just as a bare PCB. It doesn't have all the parts on it, but it becomes a talking point, because what I can do is I can show them one with all of the parts loaded and say, you know, this business card is actually a data logger with USB interface and it's got a sensor and that sort of thing. And it really gets their attention. But you give them just the blank business card without the parts on it, and you can still explain it, and you can say, here's my business card, and by the way, this is actually a circuit board, and if you have all the parts on it, you can plug it into USB and talk to it with your computer, and people go, oh wow, that's really cool. So it's just novelty, no real reason other than that. And K-Man asked, are you using them in your home automation system at home? I'm not sure what that is referring to, but the business cards? No. Actually, I should. That would be cool. I ought to connect one up and just have it say that it's reporting values back to MQTT, and then I could have a business card as part of my home automation system. Kevin Smith asked, what's the approximate length of the longest cable run between wall light switch and Arduino controller in your home automation system? What that is referring to is my current architecture, where I have light switches, which are essentially buttons on the end of a long cable that goes back over a Cat5 twisted pair cable to a switchboard location or a little rack where I've got a controller which is connected to lots of light switches around the house, and it can detect when a button has been pressed. The longest cable, I haven't actually measured it. I just have to estimate based on, you know, how far I think it's traveling. Thinking about the longest one, it's probably about 10 to 15 meters, I would guess. My house is divided down the middle into two zones. So I've got a light switch controller at each end of the house, and then the light switches in half the house are wired to that controller and in half to the other. So I don't have cables that run from one end of my house, like diagonally to the far corner, across the entire footprint. That would end up with cables maybe 25 meters long by the time you account for, you know, going up and across and back down and that sort of thing. But yeah, I guess probably 10 to 15 meters. I've never had any reliability problems with them. I've had them in for years now, and I have many people say, oh, you'll have problems every time there's a thunderstorm and you'll like blow the inputs on your devices, and nothing like that has ever happened. And that doesn't now this is not necessarily saying it's a good design principle, and ideally there should be something like static protection and, you know, lightning protection on the end of the cable. I haven't had it. I did it as a very quick and dirty solution, and it's ended up being reliable. It's one of those classic things of making a prototype and putting it into production. So yeah, blah blah blah. So down some questions. Okay, so David Watt said, your projects are so well organized in Eagle. I have several temp folders and board and schematic files outside of folders. Yeah, that can be quite tempting to do. I end up being fairly disciplined about version control for everything. I maintain all of my project files in Git, and whenever I do releases, like if I send board files off for production, I always increment the version number that's in the schematic and on the PCB on the silk screen, and I tag it in Git with the release. I've got a whole production checklist of things that I do, and part of the reason for that is it's very easy to go down the track of making copies of projects and then making some changes over here, and then you lose track of which one is which. I think part of this discipline is that I spent so many years doing software development as part of a team, and we were using Git. Well, we went through a sequence of different version control systems, including Subversion and that sort of thing, but we ended up for many years using Git. And working as part of a team, you need to make sure that you have the correct workflow and you branch off and then make your changes and then everything merges cleanly, and you have stuff that's staged for release, and you might have a version of the software that's sitting on in your test environment and then it's staged to go out to production servers. So there's this whole workflow around it. And I think I just got so used to doing that in the software environment that I've ended up doing it in hardware as well. So I maintain complete history of all the projects. And the other big advantage of it is that I use this for reporting for the R&D tax incentive. The Australian government has an R&D incentive program where if you do research in particular areas and then you submit an application, you can get a rebate on your tax for, it's complicated, I won't go into it, but basically you get like a percentage rebate against the input that you spend on those research activities. And that can be used to offset tax losses and things. Well, it generates a tax loss that you can use to offset taxable income. So part of doing that is that you need to report all of your activity. And so during the year, I've become quite disciplined about recording everything. And what it means is that when I'm generating my R&D tax application, I can run scripts against Git that pulls out information about all of the different commits that were done, when there was work that was done, and then I can categorize the work and put it into projects and etc. do my tax application. That's the reason for that. So Unexpected Maker said, so is the ESP running a different firmware? This will be in relation to the Core SP being a drop-in replacement for the particle photon, and the answer is yes. So, running a different firmware. No, it is just pin compatible running ESP-8266 firmware. That's correct, because the firmware on the particle photon is, well, it's just set up for that. Now the thing is that with particle photon, it's based on the Arduino environment. So if you're doing ESP-8266 development in Arduino, most of it is just copy-paste. It'll work. There are some slight exceptions to it, but for the most part, it's fine. What you don't get is all of the cloud management. So you don't have the ability to go into a dashboard, select a target device and say, reflash. And now that device, which might be, across the room or halfway around the world, will update to the latest version. So that is really the huge advantage of the particle ecosystem. You get all of that cloud management stuff, and the dashboard is part of it. So we got more highs from Quebec in Canada and from Germany. Quebec. It would be road building season over there right now. I've been over to Montreal. Did some work over there quite a few years ago, setting up a room managing. Backing up. Big refrigerant compressors that are used for industrial level air conditioning systems, like in high-rise buildings and things. There was a company that wanted to be able to control them via the internet, and I went over to Montreal a couple of times and helped set up a big control room, and it was deliberately set up to look a bit like NASA mission control. So it had big curved benches with screens mounted in them, and there was a glass wall, so visitors could stand behind the glass wall and see this big control room. And the control room itself was showing real-time data coming off air conditioning systems all over the world, and it would allow control of them as well. And I worked on the design for the internet connection for the air conditioners and the control system and the data logging system and storage. So we were using MySQL to record all the data coming off them and then charting all of the information in real time. It was a pretty cool project. So I went over to Montreal a couple of times to work on that. And there are some fun stories about that I won't get into. But one thing that someone said to me when I was over there is that there are 4 seasons in Montreal. They are winter, 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 and road building. That's because there's only this little narrow window of opportunity when the weather is good enough that you can actually work on the roads, and the rest of the time it's just freezing cold. So right now is probably road building season over there. Good night from Barbados. Good night, Barbados. That should be nice and warm. And oh yeah, Toby Rob. Hi Toby. So hi from Guyana, South America. Okay, cool. And 3D Gusner says, have you seen Sensor IoT from Andreas Spears, a central OTA platform? No, I haven't seen that. I'm very familiar with Andreas's videos, but I need to look up Sensor IoT. That's a good tip. Thank you. Oh, and he from Florida. So I'm going to bail on this live stream now. Thanks everyone for hanging around, and I hope this was interesting. Next time, if I plan this, what I'm thinking of doing is maybe doing live streams every second Sunday morning. Seems like a reasonable time, and then still try to get some other videos out as well, and keep working through projects and looking at how they work and what might be interesting. Hopefully what I'm doing is useful, and that you can see projects that have already been done and why things were done in a certain way. So I will do my best next time to have a look at what projects will be coming up in the list, and I'll grab the hardware and find it in advance so that I can actually show it to you for real. So thank you very much for sticking with me through, what is this now, coming up to a 2-hour live stream. I hope you have a fantastic weekend and go and build something cool. See ya.